All right, let's actually put this to use now, theorem 2, and let's take a look at this example 2. So example 2, we're asked to evaluate the triple integral over w. Our function f of x, y, z that we're integrating is z. So if we try to relate this to the above theorem, theorem 2, if we're going to relate this example 2, then this function z, that's our f of x, y, z. So for us, I can write this above if this helps. Our function f of x, y, and z, that would be equal to z. And then w is the region that is bounded between the plane z equals x plus y and z equals 3x plus 5y, lying over this region here. So, to do this problem, we have to think about what's going on visually. So now, when you have two planes that intersect in 3 dimensions, when two planes intersect, that doesn't section off a closed, bounded region of space. Contrast that with what happened up here. If we take two elliptic paraboloids, two bowls, and we intersect them, they do close off this region here. It's like completely closed off from the outside. But if two planes intersect, that doesn't close off anything. So that's why there's this little extra bit here that helps us actually hone in on exactly what is this volume that we're integrating over. So what we do know here is that we only want to be integrating over this region. And then, so this region above the xy plane. So that's the two-dimensional spread, so to speak. But then that third dimensional, the change in z, is going to be by these two planes. So what we need to do is first figure out which plane is bigger. So, and when I say bigger, that kind of is a little ambiguous. What I really should say is not bigger. What I mean is over this rectangle in the xy plane, which plane has the larger z value, right? So, first let's think about this. Let's go ahead and actually first draw in the xy plane the region that we have. So this would be from 0 to 3 in the x direction and 0 to 2. So let's say this is 1, 2, 3, and 1, 2 in the y direction. So then we have a rectangle here. So this rectangle is going to be the domain of integration in the xy plane. At least the domain of integration for the double integral here. What we need to know is which surface is above the other. So what's the top surface? What's the bottom surface? So the easiest way to figure out which surface is above another surface is to figure out where, if anywhere, do the surfaces intersect. So first find where do the surfaces intersect. The planes intersect at, or let's say instead of at, let's say when they're equal. So this would be x plus y equals 3x plus 5y. And in that case, we will have 0 equals, actually, let's solve this for y. So 5y, this would equal, or excuse me, I should say 4y. 4y is equal to negative 2x. So y is equal to negative a half x. So negative 1/2 x, if we sketch this, negative 1/2 x actually comes through like this. Oops. So this is the line of intersection of the two planes. So what this means is the only location where the planes are equal is on this line. And since we're only interested over this rectangle, where does this line and rectangle intersect, if they do at all? Well, only right here. So at this lower left-hand corner of our region D, right here, the planes are equal. So what this means is over here on this side, one plane is above the other. And then on this side, they flip and it's the opposite. What's important here is the fact that this line of intersection, this is the switching point. This is the line where on either side of this line, if we were to plug in a point over here, the one plane's above the other. And if we plug in a point over here, then the opposite's true. If this line were to have gone through our region, then this means we'd actually have to split up our triple integral into integrating over the one side and then integrating over the other side. Why? Well, because on this side we would have the one z value is greater than the other z value, the other plane, and then over here we would have the opposite. So on the one side, we would have a different order here. So effectively, our bounds for the inside integral would be different in two different regions, so we'd have to split this up. Effectively, what we would say here is that our region is not z-simple. In this case, however, our region is z-simple. So because our region is z-simple, let's see, I'll just say that our region must be z-simple. And in particular, we need to know which plane is above the other. Well, I know, since this is the line of intersection, we can pick any point we want over here, and we can just check and see which one has the biggest z value. Whichever one does, that means that's the plane that is above the other. So what can I do? I'll just pick a nice point, 1, 1. I don't want to pick 0 because that lives on the plane, on the line of intersection, in which case we get the same value. So we want to pick a point safely on this side, which I'll just pick for my test point 1, 1. So in this case, I'm just going to say 1, 1. So let's go up here and just plug in 1, 1. So at the point 1, 1, this z value is 2, and this z value is 8. So clearly, 8's bigger than 2. So what this actually tells us is, so let me write it formally here, x plus y at the point 1, 1, that's equal to 2, and that's less than or equal to 3x plus 5y at the point 1, 1, which is 8. So this implies, since our region is z-simple, this must mean that x plus y must be less than or equal to 3x plus 5y on our domain D. So this effectively tells us that this is z1 and this is z2. So our region, so what we can say effectively now is that z is bounded below by x plus y and bounded above by 3x plus 5y. And then we have y is bounded between 0 and 2, and x is bounded between 0 and 3. Which now tells us that we can set up our triple integral. So the integral from 0 to 3, integral 0 to 2, integral x plus y to 3x plus 5y, z dz dy dx. That's the integral set up. And once we have this set up, we really just need to worry about integrating this inside integral first. So this would become 1/2 z squared between x plus y and 3x plus 5y. dy dx. Integrating this, I can pull the 1/2 out. 0 to 3, 0 to 2. This would become 3x plus 5y quantity squared minus x plus y quantity squared dy dx. There's a bit of algebra involved here in foiling this all out. If you go through all of that and FOIL it out, then you just have a regular old double integral, which we know how to calculate by now. So the answer is 294.